Find and classify the critical points of the following function, f of xy, 1/3 x cubed y squared minus 7x squared y plus 24x minus 9y. Now the find and classify problems, there's really just a very simple pattern and routine. And so once you nail the pattern down, it's very straightforward to do these problems. Because there's really two stages. There's the find stage, there's the classify stage. So the find stage always runs the same way. The find says, look at your partial derivative set equal to 0. So in our case, we would have f sub x, derivative with respect to x, well, we'd get x squared, y squared. Go to the next term, minus 14xy. Then to the last term, plus 24. And then the 9y goes away. And then f sub y, well, that would be 2/3 x cubed y minus 7x squared and minus 9. And so you take the partial derivatives and you set them equal to 0. Okay, so that's how you always start. And then the next thing is you say, okay, now that I have my system of equations, we have to solve. And there's only a handful of tools you have. There's factoring and substitution. And between the two, you always prefer factoring. Factoring is a really nice thing. So we take a look at these two expressions and we say, okay, does either of them factor? Well, the f sub y is kind of hopeless. X cubed y, there's not a lot you can do there. So let's look at the first expression. What do you think? Can we make the first expression factor? X squared y squared minus 14xy plus 24. Oh, someone's very, yes. Okay. Kind of know that's what the answer is given my build-up here. It may not be immediately obvious how it factors, but there are a couple things you can look for. Look for things that are common. That's the easiest way to factor. But another thing you might notice is like, oh, x squared y squared is like xy squared minus 14xy plus 24. So if you said, oh, wait a second, instead of thinking of like x as something or as y as something, think of it xy as your basic unit. So if it throws you off, this really is the same problem as a squared minus 14a plus 24 equals 0. Now, does that factor? Well, hopefully. I mean, it's a quadratic. And the rule of thumb is almost all quadratics factor in calculus. Or at least in this calculus they do. So I'm looking for two numbers that multiply together to give me 24, but add together to give me 14. 12 and 2. So a minus 12, a minus 2. But remember, a was just sort of a placeholder. So xy minus 12, xy minus 2. So we get two possibilities. One possibility is that xy equals 12. The other possibility is that xy equals 2. All right. So from the first equation, we've narrowed it down saying whatever our points are that are critical, it has to be that either x times y equals 12 or x times y equals 2. Now, that's just the f sub x. We go and say, let's use it for f sub y. How do we use it? Well, one thing you can do is I could say, well, let me solve for y and substitute. But there's another way you can think about it. You could think of this f sub y as saying it's really 2/3 times x squared times xy minus 7x squared minus 9. And now we can say, all right, there's two possibilities. Suppose we say xy equals 12. Let's look at that possibility. Well, if xy equals 12, this becomes 2/3 times x squared times 12 minus 7x squared minus 9 equals 0. Now 2/3 times 12, that's 8. Okay, all right. 8x squared minus 7x squared minus 9 equals 0. Well, 8x squared minus 7x squared, that's pretty easy. That's also known as x squared. So really you get x squared equals 9, which tells you that x equals 3 or negative 3. So remember, if you have x squared equals 9, you get that plus or minus possibility going in. And remember that we said x times y equals 12. So if we're making a list of points, where can we make a list of points? We'll make a list of points here in the corner. Here's our final answer. 3 is our x value. Then 3 times y equals 12, so that would be y should be 4. And then if I have negative 3 as my x value, negative 3 times y equals 12, so y should be negative 4. So those are two critical points. Now that's assuming that xy equals 12. What if xy were equal to 2? Well, if xy were 2, this would become 2/3 x squared times 2 minus 7x squared minus 9 equals 0. Now, a little bit more challenging. 2/3 times 2 is 4/3, and of course negative 7 is negative 21/3. So this becomes negative 17/3 x squared minus 9 equals 0. Well, that's not looking very promising. It says, for instance, if you rearrange it, that x squared would have to be negative 27 over 17. So what does that say about x? Yeah, there's no solution. Because in our class, we're keeping it real. Now, if you allowed for complex numbers, okay, maybe you could get a solution, but in our class, we're keeping it real. So that means there's no points. And that can happen. It can happen that you might run into a situation where nothing works out. So that's it. Our full list is just those 2 points. So we're done with the find. But we're not done with the problem, because now we enter phase 2, classify. So how does classify go? So classify always starts the same way. You need to find your second order derivatives, because the classification comes from the second partials test. So we're going to look at what we call this D, which is really, I think the reason they call it D is discriminant. It's fxx fyy minus fxy quantity squared. So we have to compute these second order derivatives. Okay, so fxx. So we go through, that'd be 2xy squared minus 14y, and then fyy would be 2/3 x cubed, and that's the only y. So that's good. Subtract fxy. So I can come up and take the derivative of the f sub x with respect to y, or the derivative of f sub y with respect to x. I'll get the same answer. So if I take the derivative of f sub x with respect to y, I would get 2x squared y minus 14x. So now there's the D. So we're not quite done. The next thing is to take our critical points, and only the critical points, and plug those in. So we plug in 3, 4. And we patiently work through it, what we have. So 3, 4. So that's going to be 2 times 3, which is 6, times 4 squared. Well, that's 6 times 16, which of course, 96, minus 14 times 4, which is 56, times 2/3 times x cubed. Well, 3 cubed. So 2/3 times 27, which is 18. Now we're going to subtract. Oops, I forgot my square. Ha ha ha. Don't forget the square. That's important. Subtract. Okay. 2 times 9 times 4. And 2 times 9 is 18, times 4, 72. Minus 14 times 3, 42 squared. So what do you get? You get 40 times 18, subtract 30 quantity squared. Now, you might think, that looks tough, but it's not so bad. there's a couple things you can do. You could say, well, 40 times 18 is 720. But if you don't like to do those kinds of computations, you can actually say, look, all I care about is the sign. And so you can start pulling common factors out. So if you weren't sure what was happening, I could say this is 40 times 18 minus 30 times 30. And I could say, hey, I can pull out 10's a common factor. So I'll pull that out. And then if I did that, that would be 4 times 18 minus 3 times 30. So I pulled out a single 10. And I could say, hey, I can pull out a 9 because there's a 9. There's a 9. So that would be 10 times 9. And then I'd have 4 times 2. And then here it would be minus 1 times 10 because I pulled out 3. And now, this is much easier to compute. So if you're having a hard time with the computation, pull out common factors. Because we don't actually care about the value. What do we care about? We care about the sign, whether it's positive or negative. Now, I don't need to worry about these numbers. I worry about this quantity. 8 minus 10, is it positive or negative? It's negative. So the whole thing is negative. Now, when your discriminant, your d, is negative, what does that say about your critical point? It's a saddle. And if you go through and do -3, -4, well, let's see, we'll try to do that one a little bit faster. What happens? Well, what happens is, if you look at this first term, it will flip the sign. Because there's a negative and a negative squared, so it's going to become negative 96. The next term will also flip the sign, that's a plus 56. 2/3 x cubed, well, I'm just going to flip the sign, so that's going to become negative 18. Then I'm going to subtract, and again, just what happens here is all the signs flip. Well, but if I have a negative and a negative, that really says, hey, this is the same thing as before. It's really 40 times 18. This is really going to be the same as 30 squared. So it's the same numbers. So it's still negative, which means it's still a saddle. And therefore, this point has only 2 saddles. And that's the only kind of critical points we have. All right. Good. Well, hopefully, if there's one on the exam, it'll be more interesting than just a bunch of saddles. Yeah, we'll see. We'll find out next week. So, what are we after? We've talked about the second partials test, and the second partials test is really wonderful if you want to say whether something is a local max or a local min. Because the second partials test only says, hey, let me use the local behavior to explain what this point is doing. But maybe you're not after a local max or a local min. Maybe you're after a global max or a global min, or what you might call an absolute max, absolute min. So how do we find those? Well, before we find them, we've got to acknowledge that there's a problem, and that there might not be one. It's possible that there is no global max or global min. And before you think that, well, surely those kinds of functions are very complicated, let's do a simple example. Suppose I have the function x plus y. That's a fairly straightforward function. And the domain is a nice domain. So we're going to have x goes between 0 and 1, and y going between 0 and 1. So if we were to sketch our domain, what it is it's a square without including the edges. So it's a dashed line, and then our domain is all the points here in the interior. Now, what is the global max or the global min? Well, where would we look for finding a global max or a global min? Suppose you just said, my function is x plus y. I have this square, and I wanted to make x plus y big. Where should I be looking? I should be looking in that top right corner. So the top right corner, that's where both x and y are large. So x plus y would be very large. Now the problem is, where do I pick? Because if I pick a point, is that going to be the point where the function attains a maximum value? And the answer is no. Why? Because I can get closer to the corner. You say, okay, well maybe that's the point. No, because I can get even closer to the corner. You might say, well, okay, well, then just go to the corner. But why can't we do that? The corner's not in our domain. So we can get closer and closer to this corner, and we know that in the corner, that's where we have our largest possible value, but we can't ever actually attain the corner. Similarly, if I wanted the smallest value, I'd say, well, head downstairs. But again, I can get closer and closer to that bottom corner, but I can never actually reach it because it's not part of the domain. So we have the problem in that not all functions will always have a max or a min. But it turns out if we add some assumptions, in particular about the domain. So our problem is really the domain. So if we have a function which is nice, and our definition for nice is going to be continuous, and our domain is nice. So domain being nice in particular means closed and bounded. So we've mentioned these words before. So the word closed, that says I'm going to include my boundary. So if I want to get closer to the boundary, I say, yeah, just go to the boundary. That's part of your domain. That's what the closed means. I include my boundary. The bounded part says that I can take my whole domain and put it inside of a big circle. So in other words, I don't continue forever and ever. I can put it inside a single big circle. So if I have a continuous function on a closed and bounded domain, it must achieve a global max and a global min, or what you could call an absolute max and absolute min. Now we're not going to prove this fact. This fact takes a couple of years of undergraduate math classes to get to proving this fact. If you want to learn why it's true, I strongly encourage you, become a math major, and 4 years from now you'll be like, oh, that's why it's true. It's good stuff. It's good stuff. But we're just going to take it as a fact. Now here's a really useful thing about this fact. We know our global max and global min exist. That's a huge advantage. Massive advantage. So here's what we're going to do. So here's the process for finding a global max and a global min. So what we're going to do is we're going to say, now that I know it exists, I'm going to start by first off making a list. So the making a list part, that's really what we have right here in steps 1 and 2. Say, I know there's a global max or a global min, and what I'm going to do is I'm going to go through and I'm going to check every single point where it could exist. So this is going to be making a list where I might have the global max and global min. Now, how do we make such a list? Well, the answer is we go back to what critical points are. Because if we have a global max or a global min, it has to be a critical point. So there's sort of two places you should be looking. So one place you should be looking is in the interior. So this is the shaded part here. The interior, that's where you say, is the gradient 0 or is it undefined? All right. So those should be on your list because it might happen that your max occurs on the interior. The second place to look is on the boundary, because remember we said critical points, gradient is 0, gradient is undefined, or you're at the boundary, because in the boundary you have that inability to move freely. There's restrictions. And so you work on the boundary. Now how do you actually work on the boundary? Well, the beautiful thing is if I have a two-dimensional domain, then the boundary, let's sketch a different part. So maybe this is our domain here. So the interior, that's where we do gradient equals 0, gradient is undefined. And the boundary, this edge here, it's a one-dimensional object. It's essentially a curve. And now we say, hey, we have tools to figure out where max and mins can occur in one-dimensional objects. And so we use those tools. And one thing, don't forget your corners. Always throw them in. That's probably the first thing you always put in your list, because it's easy to forget the corners because you're just getting so excited and all the work that you get to do. You forget, oh yeah, the corners. Got to check those as well. No. So we've made a list of where they can occur. Now that we say, okay, here's a list. It's going to be a relatively small list. We're not going to check infinitely many points. Maybe we'll have a half dozen, maybe 10. We say, our max or min occurs somewhere on this list. So we check each point. And the way we check it is we plug it into the function. So we evaluate. And now, once we've evaluated, we just read off the answer. Because we said, we know the max or min occurs, and we found the points where it could occur. We checked what all the values of the functions are. The largest one, that's going to be the max. And the smallest one is going to be the min. All right. So that's the process. So we're going to go through and work through some examples. And hopefully we have enough time to do at least one. No. We probably can do at least two. Okay. Any questions about the process before we start into the examples? All right.
It's asked for critical points.
Sure.
Global min and max is a critical point.
Well, so
that would be included. So, like if it says find and classify.
Well, so when you're doing find and classify, that's a different type of a question. So find and classify is always about local points. And so you might say, okay, so why are we still doing the same thing of looking for critical points here? Well, it turns out, fun fact, the reason why we care about critical points is if I'm at a global max, then it turns out that I'm also at a local max. Because if I'm bigger than everything, I'm definitely bigger than everything nearby. And so that's why we also grab these critical points, because oftentimes these critical points from where the gradient equals 0, yeah, that's when we do local max or min. Now you might say, when I'm doing step 1, do I have to classify? The answer is no. That is a waste of time. And you might say, find yourself in a situation where you only have 75 minutes, and you might have to answer a collection of questions in that 75-minute period. And so you say, look, I'm not going to do anything that's not going to help me. So when you're doing this problem, you never do any classification. Classification is out. There's never a second partials test when you're looking for global max and global min. And so how do you know if you're doing a problem about global max or global min? You look for the words global max and global min, or absolute max, absolute min. That's how you know you're in this problem. All right? Okay. Well, I should say on a side note that there's sort of an easy way to remember the process. It's sort of like the classic song that you might remember. And it goes like this. You're making a list, checking it twice, gonna find out which points are nice. Absolute max and min are found. Okay? That's what you do. You're gonna make a list. Make sure. Oh, thank you. Make a list. Make sure you got everything. Plug it in. And then you got your answer. Okay, here we go. Find the global max and the global min for f of xy is x squared plus 2y squared minus xy minus x minus 3y for the domain x goes from 0 to 5 and y goes from 0 to 3. So I'm going to give a quick sketch of the domain. Turns out it's easy to draw this one. What does it look like? It's a rectangle. So there's 5, there's 3, and there's our domain. We include our edges. Okay, so our process. We're going to make a list. So here is our list. All right, now the way I always like to do the list is I always just throw the corners in at the very beginning, because I know the corners are always going to be in my list, and so it gives me sort of a feeling of accomplishment. Like, I'm making progress. I'm contributing to my answer. So, you know, it's good to have that sort of moral boost at the beginning. Plus, well, yeah, at least I know I get a point for doing the problem, because they're always going to check if you check the corners. Okay, so I've got the corners done. Now let's do the interior. So the way we handle the interior is the gradient. And so we take our gradient. So let's do that. Gradient of f, that's 2x minus y minus 1, comma, and then 4y minus x minus 3. Now, never undefine this gradient. Almost none of the problems you'll see will have that. And okay, so we set it equal to 0, which means that we set the first term equal to 0 and the second term equal to 0. So we get really our classic system of equations. 2x minus y equals 0, and then minus x plus 4y equals 3, if we just rearrange our equations. So, well, now you can solve it pretty much any way you want. I like to solve, when I have a system of linear equations, I like to scale the systems so that I can combine them together to cancel. So as an example, if I take my second equation and I were to multiply that by 2, that would be minus 2x plus 8y equals 6. And now I were to add these two together, we would end up getting that the 2x and minus 2x cancel, and then 8y and minus y is 7y, and 6 plus 1 equals 7, which says that y had better equal 1. But we also know that 2x minus y, so minus 1 equals 1. So 2x had better be 2, which says that x equals 1. Which means that in the interior, there's only one place where the gradient is 0, and it's at a very convenient location. It's at the point 1, 1. So we add that to our list. And I'll go ahead and mark it. There we go. There's 1, 1. So now we have our interior is done. No other point in the interior needs to be examined, because we know for sure that no other point in the interior can be a local, well, no other point can be a local max or a local min. And if it can't be a local max or a local min, it can't be a global max and global min. So now that we've started the problem, the easy part's out of the way, time for the fun parts, the boundary. Well, how many pieces of boundary do we have? 4. So we get to do 4 problems, 1 for each piece of the boundary. So pick a boundary. You got the left, right, top, bottom. What do you want? Bottom? Okay, so let's think about the bottom. What's true about points on the bottom? Y equals 0 on the bottom. So when we're doing the bottom, what we say is our function, instead of thinking of it as f of x comma y, I can think of it as f of x comma 0. So that becomes x squared plus 0 minus 0 minus x. Now I can think of this as a function of a single variable, x, because it's a function of a single variable, x. So we take the derivative. What's the derivative of x squared minus x? 2x minus 1. Take the derivative, set it equal to 0, and you get x equals a half. Which says, there's a point right there. X equals a half, and we're on the bottom, so we know y equals 0. So 1/2 comma 0. All right, one side down, 3 to go. What side do you want to talk about next? Sorry, what? Top? What's true about things on the top? Y equals 3. So for the top, we can say our function can be rewritten, as f of x comma 3. So everywhere I see a y, I'm going to write 3. So x squared plus 2 times 9 is 18, minus x times y, so that's minus 3x, minus x, minus 9. Or if you like, that's x squared minus 4x plus 9. Again, it'll become a function of a single variable. Now do your optimization. Take the derivative. What does it become? 2x minus 4. We set that equal to 0. What point do we care about? X equals 2. So there's a point somewhere, roughly here-ish, x equals 2. So that's at the point x equals 2, and we're at y equals 3, 2, comma 3. All right. 2 down, 2 to go. What's next?
Left side.
Left side? What's true about points on the left? X equals 0. So what will happen is on the left, we're going to have f of 0, comma y. So everywhere where I see x equals, so everywhere I see an x, I put in 0, and what do we get? Well, get a 0, and then a 2y squared, and then a 0. What? Oh yeah, 0, 0, minus 3y, yes. So, take a derivative. 4y minus 3 equals 0. So what is y? 3/4. So we're at x equals 0, y equals 3/4. So we get a point. 0, comma 3/4. All right. Well, process of elimination. I'm pretty sure I know what's coming next. The right.
Could we just be using a partial y and plugging in for values?
Well, essentially what we're doing is we're looking in a slice, and we're trying to optimize in a slice. So yeah, it is a partial f, partial y. For right now, but we're going to see something in a little bit. Not on this problem. But problems are coming. Problems, my friend. We got problems right here in Ames City. Okay, f of 5, comma y. Okay, so 25 plus 2y squared minus 5y minus 5 minus 3y. So that becomes 2y squared minus 8y plus 20. Taking our derivative, what does that become? 4y minus 8, set it equal to 0. So we get y equals 2, which means that there's a point roughly there. So we are at 5, comma 2. Okay. All right. So we've made our list. Now we're going to check it. Yep. Okay, good. But no, you should go through the process. You should say, did I check the interior? Did I make sure to include the corners? Did I check every part of the boundary? And so, yeah, we said we got the corners. We did the interior, that was the gradient, and we checked each one of the boundary curves. Now you might have said, well, how did the corners enter in? Well, it turns out that we were kind of cheating when we did each boundary curve, because we said, well, we're just looking for where the derivative is 0. But because it's an optimization on a closed bounded set, we also have to include the endpoints. So the endpoints of the boundary, that's why you include the corners. Are we done? No, not with the problem. We're done with the list. We've done step 1 of the, well, steps 1 and 2. What's the next thing to do? Plug them all in. That is correct. So we have to plug in every single point into the function and evaluate. Now, some points are fairly easy to plug in. For example, 0, 0 is 0. That one's not so bad. 0, comma 3, well, that'll be negative 12. Now, you plug, how do you get that? Well, you just plug in x equals 0, y equals 3. Did I do that right?
18 minus 9 is 9.
Oh, yeah. Sorry. Yeah. This is not negative 12. Sorry. Double check. 9? No, I think it's 6. Because you get 0, 18, 0, 0, 9. 9? Now you're making me question this. What's going on here? Why are we getting something like that? Because of math? Yeah, okay, yeah, no, it's definitely 9. It's definitely 9. No doubts. No doubts. Of course it is. 5, comma 0? It's 20. 5, comma 3? That's Well, what I'm doing is I'm looking at the boundary here. So f of 5 comma 3, I could just plug 5 into here. So if you do that, 25 minus 20 is 5, plus 9 makes 14. So x equals 5, 5 squared minus 4 times 5 plus 9. F of 1 comma 1, well, nice thing about 1 comma 1 is you just plug in 1 plus 2 minus 1 minus 1 minus 3. So that's 3 minus 6. So I think that should be, sorry, 3 minus 5, negative 2. All right, f of 1/2 comma 0, negative 1/4, because I can put in 1/2 here. A half squared is a fourth, minus a half, negative 1/4. F of 2 comma 3, if I put in x equals 2, because I'm at 2 comma 3, that's a 4 minus 8 plus 9. Well, minus 8 plus 9 would be 1, plus 4 makes 5. 0 comma 3/4 is a number. Okay, so 3/4 squared is 9/16 times 2 would make 9/8. Then we're going to subtract 9/4. 9/8 subtract 9/4 is negative 9/8. And 5 comma 2, I can put in 2 here, and you'll get 8 minus 16 plus 20. 8 minus 16 is negative 8, plus 20 is 12. Okay, so now are we done? No, but we've made our list, and now we've plugged it in, and now we scan our list and say, what number is big? Well, which number is big? 20. So 20 is our global max. And then we also keep scanning and say, which one is small? Negative 2. So that's our global min. And now we are done. So that's the process. It can be a little bit tedious, but it's sort of methodical, so be patient. Usually we end up trying to get nicer points. Okay, now that we've done that one, let's do one more. Find the global max and the global min for g of xy equals x squared minus 4x plus 2y squared minus 4y plus 1 for the domain, which is a triangle with the vertices which are at 0, 0, 3, 0, and 3, 3. So 0, 0 is here, 3, comma 0 is there, 3, comma 3 is there. All right, so our triangle, we can sketch that in. I'll use a different color here. Looks like that. And we're going to include the boundary. Sorry, all the points inside. So there's our domain. Okay. Now, same process. Make a list. Now you see why I like to include the corners first, because I feel like, yes, I'm making progress. Okay, let's include the corners. Where are the corners? 0, 0, 3, 0, 3, 3. Okay, well, after the corners, what do you want to check? Check on the inside. So what do we do to check on the inside? Take the gradient. So what is our gradient of g? Well, 2x minus 4, and then 4y minus 4. And we're going to set that equal to 0, which really means it's a 0 vector. Well, this one is probably a little bit easier to solve. When does 2x minus 4 equal 0? X equals 2. When does 4y minus 4 equal 0? Y equals 1. Now, should we include the point 21 on the list? Let's actually ask that question. Should we include the point 21 on our list? And you're probably like, of course we're going to include it. That's what you have to check. See, 2, 1 happens to be roughly here. So we would include that. Now what if it had ended up being 1, 2 over here? It's out of the domain. So when you're taking your gradient and you're setting equal to 0, once you get a point out, double check, is it in my domain? If the answer is no, it's like, woohoo, I don't have to check the function there. But if it is in the domain, you do include it on the list. So 2, 1 on our list. Okay, well, we have three sides. The bottom, the right, and Mr. Slanty. So, which side do you want to do first? Bottom. What's true about the bottom side? Y equals 0. Okay, maybe that's what attracted people to the bottom side. All right, so on the bottom side, okay, this is y equals 0. So we make this f of x comma 0. Not f, g. G of, there we go, very fancy g. So everywhere we see a y, we put a 0. So we get x squared minus 4x plus 1. Take the derivative. What is it? What do you get? 2x minus 4. Set that equal to 0. And we end up with x equals 2. Again, just double check. So x equals 2. That is on the side. We could have gone x equals like 4. Don't include it. Always just double check to make sure your points are in your domain. So 2, 0. That's the point on our list. Okay, what's next? The right? Okay, on the right side, what's true? X equals 3. So our function becomes 3, y. So we're going to get 9 minus 12 plus 2y squared minus 4y plus 1, which we can rewrite this as 2y squared minus 4y minus 2. Taking the derivative, what does this become? So 4y minus 4, set equal to 0, y equals 1. So we get that point there. Whoop, sorry. So that's the point 3, 1. All right. One side left. Mr. Slanty. So on this side, it's not just simply a y equals a number or an x equals a number. It's a curve. What curve is it? Yeah. So it's y equals x. So what we do is we say, okay, so for our slanted side, we say, all right, we're going to look at g of x comma x. Right? We're going to put everything in terms of a single variable. Now, in this case, we'll put everything in terms of x. We could also put everything in terms of y. But I want to get it down to a single variable, so I can do my one variable tools. So we're going to get x squared minus 4x plus 2x squared minus 4x plus 1, which becomes 3x squared minus 8x plus 1. Take the derivative. What do you end up with? 6x minus 8 equals 0. So what should x be? 4 over 3. And now remember that we're on the curve y equals x. So that means we're at 4 over 3, comma 4 over 3. Because y and x are the same. All right, so now we're just going to make sure we did everything. We got the corners, we got the interior, and we checked each one of the sides. And 4 over 3 is roughly there. So we now have 7 points to check. Okay, what's our next thing to do? Plug them in. And nice thing, it's a shorter list. Should take us less time. We would hope. Okay. When we plug in 0, 0, what do we get? 1. 3, 0, what do we get? I think we'll get negative 2. 3, 3, what do we get? Well, if we come here and plug in 3, we get 2 times 9, 18, minus 12, minus 2. So what was that, 4? Sounds like 4. I'll put 4. 2 comma 1. What do we get?
I think our f of 3 comma 0 should be positive 2.
F of 3 comma 0 should be positive 2? Oh, we probably should write G. Yep, these are all fancy G's, because our function is G. Okay, f of 3 comma 0. If I put in 3 comma 0, it should be negative 2, I think, unless we made a mistake here, simplifying. 2 comma 1, that's on the interior. Okay, we got to plug it in. Let's see, so we'd get 4 minus 8 plus 2 minus 4 plus 1. So that 4 plus 2 plus 1 makes 7 minus 12, negative 5? Yes? Okay, negative 5. 2 comma 0. What will that be? Well, 4 minus 8 plus 1. I think that's negative 3. Negative 3, okay. 3 comma 1. So plug in 1. 2 minus 4 minus 2, negative 4. 4 thirds comma 4 thirds. Well, we can come in here. So that's 3 times 16 over 9 minus 8 times 4 over 3. That's 32 over 3 plus 1. Well, 3 times 16 over 9, that's really the same as 16 over 3. Subtract 32 over 3 is negative 16 over 3. And add 1 would give us negative 13 over 3. Now, in case you're wondering what is negative 13 over 3, that's the same as negative 4.3333333. Okay. Now, we've plugged them in. And probably this is the part you want to check twice. Okay. But in the interest of time, we're going to assume we plugged it in right. Scanning our list. Which one's the biggest number? 4. So this is our max. Which one's the smallest one? Negative 5. So there's our min. And we're done. And we really are done. That's it for now. Okay, well now let's do another problem. Find the global max and the global min for h of xy, which is 2x cubed plus 3y squared minus 12x for the domain x squared plus y squared less than or equal to 4. Now, that's a different kind of domain. What do we have? Well, x squared plus y squared less than or equal to 4. We can sketch that. That's a circle with radius 2. Now, one thing right away is you might say, hey, where are the corners? And the answer is, there are no corners. What? That's right. A cornerless problem. That's okay. We still do our procedure. It's still the same thing. So we're going to make a list. All right. Let's go through our list. Well, no corners, so we don't put that on our list. Let's start by looking on the inside. So we take here our function and take our partial derivatives, set them equal to 0, because that's our gradient. So 6x squared minus 12 equals 0. h sub y would be 6y equals 0. Well, that one is easy to solve. Y has to be 0. This other one says x squared had better be 2. So that tells us x is going to be plus or minus the square root of 2. So we end up with a couple of points now. Namely, positive the square root of 2, comma 0, and negative the square root of 2, comma 0. So if we're plotting those, square root of 2 is about 1.4. So we have a point here, and we have a point there. All right, so there are the points on the interior. What about the boundary? So the question is, how do we do the boundary? And there's a couple of ways we can do it. One thing we can say is, all right, I need to get the function for the boundary, or rather, I need to get our function, which is 2x cubed plus 3y squared minus 12x. I need to get that down to a single variable. So I want to get it down to just a function of x or a function of y. And it's probably easier to focus on the y squared part. So if we do that, well, one thing we can do is we can say, hey, wait a second, on the boundary, see the boundary, that's where x squared plus y squared is equal to 4. So what we can do is we can say, hey, on the boundary, we can rewrite this to say that this is 2x cubed plus, and I'll replace y squared by 4 minus x squared, and then there's still a 3 in front, minus 12x. Or that becomes 2x cubed minus 3x squared minus 12x plus 2. And you might say, cool, 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 cool. But there's one other thing you have to pay attention to. With restrictions on x, namely, x goes between -2 and +2. Because I can only go from there to there. So these are, in some sense, these are the endpoints. And almost always when you're dealing with boundary, in one way or another, you'll get endpoints involved. So here's our function of a single variable on the boundary, and we take our derivative. So we would get 6x squared minus 6x minus 12. And we set that equal to 0. So x squared minus x minus 2 equals 0, which factors into what? Well, factors as x minus 2, x plus 1. So we get x equals 2. So that's this point over here. So that's on our list, the point 2, 0, or x is -1. Now remember, y squared is 4 minus x squared. So if x is -1, we get that the corresponding value for y would be 3. So that gives us y equals plus or minus square root of 3. So that gets us some points over here and there. So namely at the point -1 comma root 3 and -1 minus root 3. And then we also need to include this point. Now why that point? Because it's the end point. And when we have a restriction on our choices, we have to include the ends. Alright, so there's our list. That wasn't so bad. Alright, okay, so what comes next? The answer is we plug all the points on our list into our function. So we're going to evaluate all of these in our function h. So suppose we plug in root 2. So we're going to get 2 times square root of 2 cubed. So let's see, that would be 2 times square root of 2 times square root of 2 times square root of 2. So that's 2 times 2 times square root of 2. Because square root of 2 cubed, you can combine two of those square roots into a single thing, plus the 0 minus 12 times square root of 2. So 2 times 2 is 4 root 2, minus 12 root 2 is -8 root 2. So minus 8 square root of 2. Suppose we plug in negative root 2. Well, the only thing that changes is that this part here, the 2x cubed, is going to flip sign. So it becomes a minus 4 root 2. The 0, still 0. And then here, it becomes a plus 12 root 2. So that gives us an 8 square root of 2. Now the rest of the points, all of these points here, are points that are on the boundary. So we can use the boundary function. So if we plug in 2, 0, let's see, on the boundary, here we go. Here's the boundary function. Well, maybe it's not the simplest. Plug in 2, 0 here. 2 times 8 is 16, plus 0 minus 24. 16 minus 24, -8. All right, that's good. Minus 1 comma root 3. Okay, now I'll use this one. So minus 1 would be minus 2 minus 3. So that's a minus 5 plus 12 plus 12. So that would be plus 24. So you get minus 5 plus 24, that's pretty large, that's 19. And minus 1, comma minus root 3, well look, it only depends on x, so it's again 19. How about negative 2 comma 0? Well, negative 2 comma 0, probably it's easiest to plug into the original. Negative 2 cubed, that would be negative 8 times 2 is negative 16, then plus 0, and plus 24. That would give you 8. So now, what do? Well, we start scanning. And we say, all right, where are the numbers? What's the largest number? You might say, well, what is 8 root 2? Well, the important thing is that square root of 2, it's about 1.4. It's bigger than 1, so it's definitely bigger than 8. But it's smaller than 2. So it's definitely below 16, which is also below 19. Which means that is pretty big. It's a fairly large number. So, what do we get? Well, we get the following. This is the biggest. But wait a second, which one? Well, the answer is they're both the max. So, the question is, what's the global max? The answer is the global max is 19. Now, if the question is, where do you attain the global max? The answer is, we attain it at 2 different spots. So the global max is 19, and it's attained at 2 spots. All right. What about the min, the smallest value? Well, definitely it's one of these 2 negative numbers, but remember what we said. Root 2, it's bigger than 1, so 8 root 2 is larger in size than 8, and therefore the min is this value, square root of 2 comma 0. So the min happens over here, and then the max happens at these locations. So that's it. So minus 8 root 2 is the min, 19 is the max. And all right, now here we were able to take advantage in the fact that our boundary was kind of a nice curve, a circle, and we were able to simplify our function to 1 variable. Well, what if we had a boundary where we couldn't do that? Could we still answer the question? Well, that's a good thing to ask, and we'll do that next time. All right, see you then.